into a little bit more detail of what we call the velocity selector. In this problem, we have an electron passes through crossed electric and magnetic fields. That's this area right here. The first field is 1.25 Teslas out of the page. So in this region, the first magnetic field, we'll call it V1, 1.25 Teslas. The direction is out of the page. I'm going to go with standard X, Y, Z definitions, where a positive Z is out of the page, so this magnetic field vector is plus K. Only electrons with a speed of 1 × 10⁻⁷ meters per second pass straight through. So we shoot lots of electrons in. Some are going to veer up, some are going to veer down. The ones with this speed are going to go straight through. That's the velocity selector part. They enter a second magnetic field where it strikes the sensing plate in 2 nanoseconds. So ns is nanoseconds times 10⁻⁹. So it comes into this region with a second magnetic field, no electric field in this area. So this second field is B2 equals, we don't know what it is. So part A, draw the electron path from start to finish. So what does the electron motion look like in that path? Our electron starts here, and it's shot through some potential difference. That's what gives it the different speed. So it's moving forwards. So it's going to start to move forward. We're going to draw the path of the electrons with speed 1 × 10⁷. It goes all the way forward here. As we're drawing this, you might think about why does it go straight through, or why do only ones with that speed go straight through. Then it gets to this region over here where it hits the place. Let's put an arrow for a velocity. A place with only a field into the page. Let's find the direction of the force. So the velocity is this way. So let's draw in the velocity when it enters that field. Our thumb goes with the velocity, our finger goes with the magnetic field, and we see that our finger points up for the force, but it's a negative charge. So we have to rotate our force by 180. The force points down. So there's our magnetic force when it's in the second magnetic field. This force is perpendicular to this velocity. It's going to result in circular motion, so our electron is going to swing around and it's going to whack into our sensing plate right here. So there's part A done, the electron path from start to finish. Part B, what is the electric field? So now we get into this part. This is the part that's called the velocity selector. And a velocity selector is exactly what it sounds like. It selects particles of certain velocities to pass through. Particles with any other velocities can't pass through. So let's think about how that works. So part B. So let's do a quick sketch so we're not drawing too much up there. So here's our electron when it's in the middle of that path. It's going to the right with some velocity v, 1 × 10⁷ meters per second. There is a magnetic field which points into the page. So let's start a free body diagram on our electron. It's moving to the right. Magnetic field points out of the page, that's the dots. So it says that the force points down towards the bottom of the page, but that would be for a positive charge. This is negative, so we have to rotate by 180. Our magnetic force points up towards the top of the page. FB. Okay, so that's the first thing we know, is what is the direction of the magnetic force. The second thing we know is that it goes straight through. If it goes straight through, that tells you that the acceleration has to be 0. Because if the acceleration wasn't 0, if it pointed up or down, if the acceleration pointed up, it would veer up this way. If it pointed down, it would veer down this way. If it's 0, it goes straight through. So in the y direction, it has to be 0. And in the x direction, it also has to be 0 because the speed is constant. So our acceleration is 0. If the acceleration is 0, the net force is 0. The net force is the magnetic force plus the electric force. So that tells us two things about the magnetic and the electric force. FB and FE, to get them to sum to be 0, they must be in opposite directions. So now we can draw in our Fe. And the second thing is they must have equal magnitudes. So only if these two forces are equal and opposite can the sum of those forces be 0. Okay, so we've got the direction dealt with. We know that the electric force points down. Let's deal with the fact that the magnitudes have to be equal. So the magnitude of FB equals the magnitude of FE. The magnitude of FB is going to be the magnitude of the charge times the magnitude of the velocity times the magnitude of the magnetic field. We know that force is charge times electric field, so we've got the magnitude of the charge times the magnitude of the electric field. Those Q's cancel, so E is equal to V times B. V is the speed, 1 times 10 to the 7. B is the strength of the magnetic field, 1.25 Teslas. So our electric field magnitude is 1.25 times 10 to the 7 newtons per coulomb. That deals with the size of our electric field. What about the direction of the electric field? So we know the electric force is down. And we know electric force is equal to charge times electric field. Our charge is an electron minus the fundamental charge. So this minus sign here says that the electric force and the electric field are opposite in direction. So our Fe is down, so our electric field E must be up. So E is 1.25 times 10 to the 7 newtons per coulomb J hat, where J hat points up, where we defined our electric field. Okay, part C. What is the radius of the path of the electron in the second magnetic field? So we're going to try and find that radius right there. I'll redo my sketch again, part C. So there's my electron in the second magnetic field. It swings around like this. This magnetic field, B2, is into the page. So let's get some X's there to show B2. One thing important to remember here is we don't know B2. What do we know? Well, we know the speed of the electron. V is equal to 1 times 10 to the 7 meters per second. We know how long it takes to traverse that path. That was 2 nanoseconds. So 2 times 10 to the minus 9 seconds. So how could we find the radius of the path? Well, it goes in a circle. So our speed would be distance over time. The distance it covers is a half of a circumference. So the radius of the path then will be V times the time divided by pi. So 1 times 10 to the 7 meters per second times the time, which is 2 times 10 to the minus 9 seconds, divided by pi, gives the radius of that path to be 6.37 times 10 to the minus 3 meters. Pretty small. Okay, part D then asks what is the strength of the second magnetic field. So our electron in that magnetic field is going through circular motion, so we know that the sum of the forces is mass times acceleration. It's experiencing the magnetic force, Q times V times B2, because it's in the second field. It's going in a circle, so we've got V squared over R for our acceleration. We're asked for B2. B2 is m. V squared divided by V is going to give us V, divided by Q times R. Our mass is the mass of an electron, 9.11 times 10 to the minus 31 kilograms, times the velocity, 1 times 10 to the 7 meters per second, divided by Q. This would be the magnitude of the charge because we're finding the magnitude of the magnetic field, 1.6 times 10 to the minus 19 coulombs, times the radius of the path, which we just figured out. And that gives us the size of the magnetic field, 8.94 times 10 to the minus 3 teslas. Magnetic field, of course, is a vector, so we should write it down with a direction. From the picture that was given, we know the direction is into the page, which is negative k hat. Okay, so that finishes up that section.